Okay, so starting with today's class, we're going to begin looking at digital video compression and how video is stored and how it's represented. We've already seen how images might be stored, and in many respects, a video is just a sequence of images. But it has some properties that we can exploit that makes it even more compressible than a bunch of images one after the other. So the old analog system used in Europe, but not France, was called PAL, P-A-L. And that used 25 frames per second. Kind of. A bit more complex than that. And cinema, for example, uses 24 frames per second. So when you went to the cinema, you would see 24 separate images every second. If you saw a reel of film, 24, almost like a negative roll, you would go along, you could count 24 frames, and that'd be a second's worth of movie. Now, as it happened, there are no film cinemas left in Ireland. They're all gone. I think we were one of the first countries to actually lose all the old cinemas and go completely digital. But at its simplest, video is a bunch of pictures one after the other. Depending on what you're compressing, you may vary things. I was compressing some SpongeBob SquarePants last night, and I found that 12 frames, 15 frames a second was fine. Typically, traditional animation didn't actually use 24 frames per second. It would do 2 of the same frame, and then another 2 of the same frame, another 2 of the same frame. So you'd actually have 12 frames per second, really. But for the illusion of motion, you would really need about 15 frames a second, maybe 12 or 15. And even then, if you have the camera panning very far, if it's moving a lot, you start to notice that. Now, video is big. If you consider that the screen I'm showing you now is, I think, something like 1080 pixels by 800 pixels or something like that. The minimum you would watch, say, an episode of something on your machine, on your laptop, if there was something on the internet you were going to watch, the minimum you could really tolerate for any length of time would be 640 by 480 in terms of resolution. Anything lower than that, and you really wouldn't be bothered. So if we take even the minimum for an episode of whatever it is your poison is that you like to watch on TV, 640 by 480 pixels is the minimum you'd want to go for at 25 frames per second. If you're talking 24 bits per pixel then, because it's like RGB, if that wasn't compressed, you'd be talking about 21 megabytes per second. Now, at those kind of data rates, video would be very difficult to store. There was a time it would have been impossible actually to process data rates at that kind of speed. We have faster computers now, so we could do it. So compression might not be essential, but it's certainly desirable. Even if we were to work out what a 640 by 480 JPEG might be and consider 25 of those every second, you're still racking up fairly big numbers pretty quickly. When we're talking about video compression, we talk about the compression happening at 2 different levels. So there's intra-frame compression, and that's compression that operates on a single frame. So intra means within, so it's within the frame, and we sometimes call that spatial compression. So with intra-frame compression, you're taking a picture and you're compressing it. You're taking the next picture and you're compressing it. You're taking the next frame, you're compressing it. You're taking the next frame, you're compressing it. You're taking the next frame and you're compressing it, and so on. And I mean, if a JPEG can reduce the size of a single image to maybe 30% of what it would have been, well then you can do 1,000 JPEGs and they'll be a third of the size of what they would have been. So you can think of video as a whole bunch of still images to be compressed one after the other. But it's actually when we start to consider interframe compression that the party really kicks off. So inter means between, and interframe compression exploits similarities between the frames. We sometimes call that temporal compression. So intraframe compression, basically, it's like a bunch of JPEGs one after the other. And there is even a form of video we call MJPEG or motion JPEG, where the video is stored as one JPEG after another. So JPEG, another JPEG, another JPEG, another JPEG, another JPEG, another JPEG. It doesn't have to be a JPEG, but since JPEG can come on a chip and it's already lying around and you have algorithms to do it, you might as well store them as JPEGs. However, if we consider here a shot from the news, then if we consider another screenshot a few seconds later, you can see that in that time, very little has changed. And this now is like well over a second later. If you consider that there's 25 different images every second, how much could it have changed in 1/25th of a second? I mean, she'd want to be really moving it for us to notice very much at all in 1/25th of a second. What I've done actually in this next frame is I superimposed them in Photoshop and highlighted the difference, the pixels where there's a difference, and you can see that there's some changes in certain places. I don't know why the background there changes so much, actually. Maybe it's sort of, Dublin flickering by night, whatever. So the point is that although we have 25 separate images every second, not a lot happens between one image and the next. I mean, if you had a video of me standing up here, there's not a whole lot going on, like. So it's not really 25 completely separate different images every second. Sure, if it was, your head would explode. You couldn't take in 25 separate images a second. So there are major similarities between one frame and the next frame, and we can exploit those similarities. So here I have a rather contrived example, but if we say that between frame 1 and frame 2, very little changes, between frame 2 and frame 3, very little changes as the car is driving across there, okay? We can construct the current frame by reusing parts of the previous frame. So you remember I said you can reduce, reuse, and recycle? Well, here we're going to do a lot of reusing. So if you had transmitted frame 1 and the receiver had frame 1, you could say to the receiver, look, the bits there that I'm highlighting there, the bits in red, they're the same. Just copy and paste those from frame 1 into frame 2, and then I'll give you the bits that have changed, the parts that have changed. In this case, it looks like, I don't know, maybe 20% of it has changed. So in this example, frame 2 would only take up 20% of the regular size because we're reusing we're reconstructing the rest of it from frame 1. So do you get the idea? So the receiver's already got frame 1. And the transmitter says, okay, so I want you to copy and paste these sections from frame 1 into frame 2. And now here are the bits that you can't copy and paste. Here are the parts that have changed. Get the idea? You need to keep with me now because the plot thickens considerably. So that kind of makes sense, because from one frame to the next, if we go back to the news, you know, her head is moving, her lips are moving, her coat not so much, the background behind her not at all really. So there's no point in sending this part of the image again. The receiver's already got it. So you send frame 1, you say, look for frame 2, you've already got this part here, so just copy and paste that in and you're good to go. So we're constructing frame 2 by reusing parts of frame 1. And then only for the parts that we can't reuse do we send the information that's needed. So if you think about how much of an image changes between one frame and the next in a 25th of a second, you know, you've got a lot of reuse there that you can play with. Now, typically what happens is the transmitter will compare a portion of frame 2 with a portion of frame 1, and there'll be some threshold. Like, so if it's not a perfect copy, it'll say, well, is it close enough? And that threshold, it's only then if it goes beyond that it would trigger a resend of that piece of information. So if the receiver already has frame 1, then only the information needed to update from frame 1 to frame 2 need be transmitted. So you're saving quite a lot there. So far, so good. Yeah? So you've sent frame 1, and then the transmitter would say things like, well, look, frame 2 is the same as frame 1, except for these changes. Change these parts, here, these are new parts. Frame 3 is the same as frame 2, except for these small changes. Frame 4 is the same as frame 3, except for these small changes. In some respects, it's a very elaborate form of difference coding, where you compare one sample with the previous sample and you code the difference between them. It's really just that principle taken to a two-dimensional multi-value array. So coding the difference between the frames requires a lot less data than coding the entire frame. Now, if you're saying to the receiver, look, here are the parts that are the same and here are the parts that are different, to actually address individual pixels would be too expensive. To say, you know, pixel 17,934,000, that's changed. By the time you would address the pixels, you'd have sent the information. So the image is broken up into blocks, and we consider it on a block by block basis. And then only the blocks that are significantly different from the previous frame are transmitted. Now, what does significantly different mean? Well, that's one of the thresholds you could set when you're coding. You could say, I want really high quality, so a small difference is, I'm considering that significant. If you were trying to really squeeze it down, if you're YouTube or someone, you might say, well, you know, for me a significant difference is, you know, yay big. And so only the blocks then that are significantly different will be sent, and the blocks that don't change are just copied from one frame to the next. So in this case, the transmitter would say, block 1 is the same again, 2, same again, block 3, same again, block 4, same again, 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 and so on. And then we'll say, same again, same again. Then here we'd say, okay, this block is blah, 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 whatever. This block is blah, 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 whatever. This block is blah, 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 whatever. So these 1, 2, 3, 4, 5, 6, 7, 8, these 24 blocks would be sent. But here, we're sending only 24 blocks instead of the whole image. So we can play them on a block by block basis. When things go horribly wrong, you start to see those blocks. So if you have terrestrial TV and the reception isn't great, sometimes things aren't where they're supposed to be, and you'll actually see the blocks. Or if you have a dish and a bird smacks into your dish or something, you might start to see the blocks. YouTube can get very blocky on a bad day. So it's done on a block by block basis, and sometimes we can see those blocks. Which is why I'm always fascinated by movies that have video in the future and it starts to go bad and you see all these like lines and noise and stuff, whereas in reality when digital TV starts to go bad you just see blocks and things all over the place, or sometimes the motion doesn't work quite right. Now, so far so good. So we're comparing this frame with the previous frame on a block by block basis. And if the block we're trying to code is similar enough to the equivalent block in the previous frame, we don't bother sending it, we just say that's the same as the frame before. If it is significantly different, we send it. But this happens on a block by block basis. Yeah, it is worth noting as well that you also have to account for uncovered background. Now, so if we look here in the current frame, we're trying to code this block here. And when we compare this block with the equivalent block in the previous frame, it's very different. So if we compare this frame here, this block here, with this block here, it's similar, so we say that's the same as before. This block here is the same as this block here, so that's the same as before. But this block here, for example, is not at all the same as this block here. The equivalent block in the previous frame is very different. So you might say, well, what can we do? We'll send the block. But here's the really, really clever part about video compression. Sure, the block that we're looking for is not here when we go look for it in the previous frame. But the information contained in that block that we want is actually in the previous frame. It just moved. So we would like not to have to send this block. And sure enough, it turns out we don't have to send it because the previous frame already has it. It's here. So if we could figure out where it was in the previous frame, we could save loads. Because obviously, if things are standing still from one frame to the next, well, that's a no-brainer. But even if something moves, it hasn't changed that much. Do you know what I mean? Like, I've moved from one frame to the next, My glasses, my hair, my jumper are still the same. They've just moved. So what motion compensation does is it searches around for a block that can be cut and paste from one frame into the next. So for this block, the transmitter would say, you have this block, but actually you'll find it 8 pixels over and 2 pixels up, or 18 pixels over and 2 pixels up from where you were expecting to find it. So it doesn't actually start here, it starts here. And it'll go find that block. And so the transmitter then will take the previous frame, go to that location it's called to go to, will cut out the block it needs, copy it, and stick it down. And yip-de-doo, we didn't have to send it.
Some video players have an option that lets you actually see that happening. It draws the arrows between the pieces that are the same in a frame.
It'd be fun to see.
You'll see it.
And you can use things like that then to track objects, for example. Any questions on that? I see some faces that are not convinced. Because it gets worse or better, depending on your point of view. So, any questions? So, block-based motion compensation. This works perfectly if objects move in a plane that's parallel to the camera plane. So if I was moving like this, South Park like all the time, if everybody walked like they walk in South Park, then the block-based motion compensation would work really, really well. The illumination needs to be uniform. So if I'm standing in the dark and there's a big street light here and I walk into the street light, well, I look different now in the street light. I look different in the light. So it's hard to construct light me from dark me. Similarly, if you have a scene shot in a disco or something and there's flashing lights, well, the objects in the image might not have moved very much from one frame to the next. But if they were in almost complete darkness in one frame and under green neon light in the next frame, it would be hard to construct the green neon versions of them from the almost dark ones. And of course, if I pull a rabbit out of a hat, well, you know, it's going to be hard to construct the rabbit out of thin air. If there were no rabbits in one frame. If there's a rabbit in the next frame, well, you know, how are you going to make that? So motion compensation will work if these things hold. Now, they don't always hold. So if you have a spinning globe, for example, well, it's rotating. So that's going to be a problem. But at the same time, you see, how much is it going to rotate in 1/25th of a second? You know what I mean? If I'm turning around, like, how much can I turn in 1/25th of a second? You'd probably be able to reuse quite a lot of me from 1/25th of the second to the next. So even with these constraints, it can still work quite well. It would work perfectly in this scenario. But at 1/25th of a second, you know, you're still doing quite well. Certain things are worst case scenarios. Obviously strobe lights, worst case scenarios. Spinning, flashing lights. Fountains are killer. If you're doing an interview with someone and you have a lovely fountain behind them, the video compression algorithm is going to put all of its energy into trying to track and compensate for all of those drops of water flying all over the place. And it might take away from the quality of the person's face, when actually you don't care about the water behind. And sometimes if someone has a stripy shirt or a patterned shirt, it can make life complicated for the algorithms. They move around. Any questions on that? Do you get what this means?
What does it change in?
Something hidden behind one thing or another. So if this was one frame, and then I went, surprise! Well, you can't make an iPhone, what's in this picture that you can make an iPhone out of? Nothing. So similarly, if the car was driving along and you see a flower, if we go back here, if there's a flower behind the car there, and there's a piece of tree behind it. So that piece of tree wasn't in this, so what can you do? So if something is hiding behind something else, it can make it difficult. Any other questions? So, MPEG is a video compression standard. It stands for Motion Picture Experts Group. Following on the success of JPEG, it was decided that we should try and do the same thing for video. And so there was lots of meetings and discussions, and we came up with a standard. MPEG has different kinds of frames. And what we're going to look at first of all are the I-frames and the P-frames. So an I-frame is an intra-coded frame. So it's a picture that stands alone all by itself. It looks an awful lot like a JPEG. So if someone sent you just one I-frame from a movie and only that frame, you could construct it and look at it. Now, P-frames then are different. P-frames are predicted frames, they're called. And a P-frame is made by reusing parts of a previous frame. So this frame 2 here is made by using parts of frame 1. Frame 3 here is constructed by reusing parts of frame 2. And frame 4 here is made by reusing parts of frame 3. So if someone sent you just the information in frame 3, you couldn't look at that until you had frame 2 and frame 1, in fact. Frame 5 is an I-frame, an intra-coded frame. So that's a standalone frame. And you have to have a standalone frame every so often. You can't just keep saying, well, this is the same as the last one, but with these changes. This is the same as the last one, but with these changes. Eventually, it becomes, you get diminishing returns on that. Eventually, you'd be better off starting from scratch again. And you may start again twice in a second, for example. It wouldn't be uncommon to do that. So we have an I-frame here that's a standalone frame all by itself. And here we say, okay, this P-frame, frame number 6, is made by reusing parts of frame 5. And this frame 7 here is made by recycling parts of frame 6. So when the transmitter is transmitting frame 8, it says to the receiver, look, I know you've already got frame 7. So take this part of frame 7, this part of frame 7, this part of frame 7. They're all the same in frame 8. And now here's the rest of the information you need to make frame 8. And similarly with frame 9 is made by recycling parts, reusing parts of, frame 9 is made by recycling parts of frame 8. Any questions on that?
Could frame 8 reuse something from frame 3? For example?
No. That's a very good question, but no. And the reason being, certainly it wouldn't go beyond the previous iframe, because that's really, really good quality. And you must remember as well that the closest thing we've got to frame 8 is frame 7. Frame 3 would be a long time ago by comparison. So it could it? I'm tempted to say that frame 8 could use frame 6, for example, but that you wouldn't want to do that because 7 would have better information than frame 6. But you certainly wouldn't go from frame 8 back to frame 3 because you have this iframe here, which is like really, really good quality. So it's more up-to-date information and full quality. Because of that threshold, because you're not trying to make a perfect frame each time, the quality is going to degrade over time. That's why you need that iframe to start all over again and pick up the quality. You can actually pause video and go frame by frame by frame. And you'd even notice, like the last dodgy frame, you'll notice when the next iframe comes along, you'll see the quality pick up again even. If you're really, really dedicated, you could do that. Watch some video frame by frame. And of course, the coding program you might use, the parameters, you could set all these parameters. If you have a machine at home, you could install a thing called Handbrake, and that's video compression software. And it lets you set all of these things, and you can see the effects of those. We may get around to installing them in the labs, we'll see. So I want you to have a think about this and make sure you understand it before the next class, because the plot thickens even some more. But I want to leave it here for today.